Hello, I'm Professor N.B. Hulle from G.H. Raisoni Institute of Engineering and Technology. In this video, we will try to solve the problems which are based on the magnetic circuit. I will start with the simple, which is in this case, the problem is an iron ring of the cross section 4 cm square has a mean diameter of 30 cm. An air gap of 2 mm wise is made in the ring. Calculate the MMF required to produce the flux of 0.5 milliweber in the air gap. Assume the permeability of the iron as a 500 and neglect the leakage and fringing. This is a given problem. Now here in this case, in case of the magnetic problem, that is based on the basic calculations, that is based on the calculation of the maybe permeability or maybe calculation of the MMF, maybe the calculation of the current to produce the MMF, maybe flux. All these kind of the parameter calculation. First, we have to sort out the given data. And if we are able to find out the correct given data, the calculation of these problems or such problems is not a difficult case. Now, first I will calculate, or I will sort out the given data. Then we will find out what we want to calculate, and then we will proceed for the calculation. An iron ring has a cross section of the 4 cm square. Cross sectional area of the ring is given, which is given as here. The A is equal to 4 cm square. That is 4 into 10 raised to the power of minus 4 meter square. 4 cm square is the cross section. 4 cm square, which is 10 raised to the power of minus 4 meter square. Has a mean diameter of, here diameter of the ring is given, which is given as 30 centimeters. That is 30 into 10 raised to the power of minus 2 meters. And air gap of the 2 mm wide means length of the air gap is given, that is LA is given, which is given as 2 into 10 raised to the power of minus 3 meters. Is made in the ring. Calculate MMF means here we are interested in the calculation of the MMF, that is magnetomotive force we want to calculate. To produce the flux of 0.5 milliwebers in the air gap means here the flux given is 0.5 milli means 10 raised to the power of minus 3 Webers is the given value of the flux. Assume the permeability of the iron, that is relative permeability of the iron is given, which is given as it is 500. Neglect the leakage and fringing means here in this particular case, that is total flux is very same as the useful flux. This whatever the flux in the air gap is same as the flux in the iron core. Now here first we will draw the figure and we will try to understand what we want to calculate. Here it is iron ring. Has a cross section of, means we have the iron ring with a air gap of 2 mm wide. This here I will draw the figure for iron ring having the air gap of the 2 mm wide. This it will be, the figure will be something like this. We are drawing the ring which is having something air gap which is of the 2 mm wide. It will be something like this. And then we will mention all the parameters given in the problem itself, and then we will decide what we want to calculate in this particular case. Here, in this case, given is a cross-sectional area. Here, this cross-sectional area is given. This cross-sectional area is given, which is given as 4 cm square. This is given as 4 cm square. This is centimeter square is the given cross-sectional area, which is 4 cm square. Then here the length of the air gap is given. I will go this side. Length of the air gap is given, which is given as here this length of the air gap is given. In this case the length of the air gap is given as 2 mm. This is 2 mm. This will be 2 mm wide. At the same time they have given 2 meters. 30 centimeter is the mean diameter. This is, we have the two diameters, that is one is inner diameter and other is the outer diameter. In place of that they have given the mean of the inner and outer. This is the ring, and here we are having some number of turns in this particular case, and here we are applying some MMF and we want to find out this value. Here is I current in the circuit and here N is the number of turns. Now here as far as the calculation is concerned, I will brief about the formulae. Here for the calculation of MMF we may use the two formulas. One is MMF is equal to, that is N into I. Here in this case N is not given, I is not given, that's why we cannot use this formula. The second formula for the MMF is, it is phi into S. MMF is equal to phi into S. Here in this case the flux is given, which is phi is given here, and S we have to calculate. Now how is the calculation procedure for S? I will brief and then we will work out on the calculation. S here, S depends on what? S is equal to L divided by A into mu is the formula, where this mu is again, it is mu naught into mu R. Means if we have the different material, the value of the S will be the different. Now here in this particular case of the iron ring, we have the two materials. One material is the iron material and other is the air gap. That's why the total reluctance of the magnetic path will be reluctance of the first magnetic path plus reluctance of the second magnetic path. It is very similar to the resistance here. If we have one material and other material, and if we are interested to calculate the total resistance R, it will be the addition of R1 plus R2. In the similar way, we want to find out the total reluctance of the magnetic path. Here is the reluctance of the iron path, and this will be the reluctance of the air gap. We will find out the total reluctance first, and we will use this formula for the calculation of the reluctance. Now here in this case the reluctance of the magnetic path, that is S, is equal to, this is S of the iron path plus S of the air gap. We will find out the total S first, and by knowing the S and phi we can find out the MMF. Here S of the iron path is equal to, this is L divided by A into mu naught into mu R is the formula, where L is the length of this iron path. This divided by A into mu naught into mu R. But here A is the cross-sectional area which is already given. A is the cross-sectional already given. But what is L? L is the length of this magnetic path which is not given. Means length of this magnetic path or length of this iron path, that is length of this iron path, which is equal to, they are given the diameter of this ring. Diameter of this ring minus 2 millimeter will be the length of the magnetic path. So in some cases, if this value is in terms of the centimeter quite big value, that's why we can neglect this 2 millimeter for the calculation, because reluctance calculation is approximate value. Now here in this case, if I am using this formula, that is length of the iron path is equal to, we have the formula for this as, that is pi into d. Length of the magnetic path is given by pi into d. Here this is pi into d. D is the diameter. Here pi is the constant into diameter, which is given as 30 into 10 raised to the power of minus 2 meters. We can work out this calculation, or we can work out this calculation directly. This is the length of the iron path. Directly the length of the air gap is already given. That's why, which is plus length of the, this is length of the iron path, and this is length of the air gap divided by cross-sectional area of the air gap, which is same as the cross-sectional area of the iron ring, divided by mu naught, because relative permeability is equal to 1 in case of the air gap. If I am substituting the values here, length of the iron path, which is pi into 30 into 10 raised to the power of minus 2, because pi d is the formula, divided by area. Here this is area which is given as 4 into 10 raised to the power of minus 4 meters square, which is the cross-sectional area of this iron path, into mu naught is the permeability of the free space, which is 4 pi into 10 raised to the power of minus 7 henries per meter, into mu r, which is the relative permeability, which is given as it is 500, this value, plus length of the air gap, it is 2 millimeter, that is 2 into 10 raised to the power of minus 3 meters, divided by cross-sectional area 4 into 10 raised to the power of minus 4 into this value, that is a 4 pi into 10 raised to the power of minus 7, 4 pi into 10 raised to the power of minus 7. Now here, if we are working on this calculation, if I am working on this first calculation by using the calculator, this calculation is found to be 3.75 into 10 raised to the power of 6. This is 75 into 10 raised to the power of 6. This is approximate value, because here we are cutting out its fractional part, and this is fractional part is the 10 raised to the power of multiplied by 10 raised to the power of 6, means it is not the exact value, it will be the approximate value, plus the reluctance of the air gap, which is as per the calculation it is found to be 3.98. This value is 3.98 is the value of the reluctance of the air gap, which is equal to, if I am finding its addition, this value it is found to be 7.73 into 10 raised to the power of 6. It is ampere turns per Weber is the value of the S, or reluctance of this magnetic path. And if we know the reluctance of the magnetic path, we can find out this MMF now. Here in this case, this MMF is equal to, or reluctance of the magnetic path is equal to phi into S. This is phi into S, which is very same as phi is given, that is 0.5 into 10 raised to the power of -3 into reluctance of the magnetic path is 7.73 into 10 raised to the power of +6. And if we are working on this calculation, its MMF, that is magnetomotive force, is found to be, as per this calculation, its value is 3865 and its unit is ampere turns per Weber, because this MMF is equal to MMF is ampere turns, because here MMF is its formula is ampere turns. Now here in this particular case, this is the value of the MMF as per this calculation. This is the first calculation. Now here in this way we can calculate the values of the similar problems. That is the stuff for this particular problem. Thank you for watching the video. In the next video I will discuss with the similar kind of the problems. Thank you.